Hello everyone, my name is Chetan Rawal and today I am going to give presentation on the topic of vision transformer. So let's begin with understanding why we need the vision transformer. For the decades, convolution neural network or the CNN have dominated the computer vision. However, they come up with the certain limitation. First, CNN have the strong inductive biases. They assume that nearby pixels are related with which restrict the ability to generalize the new domains. Second, CNN have limited receptive fields in early layers, meaning that they can only see the small portion of the image initially. Third, they struggle to capture the long range dependencies between the distant part of the image. Meanwhile, in the field of the natural language processing, transformers achieve the remarkable success. They use the self-attention mechanism that can capture the global context scales exceptionally well with the large datasets and have achieved the state-of-the-art result on the various language tasks. All these are without the strong architecture assumption. This success raises as an important question. Can we apply a pure transformer to the computer vision without using any convolution layer? So that this is the exactly what the vision transformer aims to answer. The motivation is to bring the power of the transformer to the vision domain and overcome the limitation of the CNN. Now let's understand what exactly is the vision transformer. So the vision transformer is commonly abbreviated as a ViT, is a deep learning architecture that applies the transformer model directly to the image classification. The key innovation is treating an image as a sequence of patches similar to how transformer treat text as a sequence of words. The architecture consists of five main components. The first, patch embedding, where we divide the input image into the fixed size patches, typically the 60 by 16 pixels. Second, the linear projection, where we flatten these patches and project them into the embedding space. The third is the position embedding, where which add the learnable position information to help the model understand the spatial relationship. The fourth, the transformer encoder, which uses the standard transformer layer with the self-attention mechanism. And finally, the classification head, which is the MLP head that produces the final prediction. Let's deep dive into the how vision transformer actually works. I'll explain this through the step-by-step process. The overall architecture follows the clear pipeline where we starts with the input image, typically the 224 by 224 pixel with the three color channels. This image is splits into the patches. For the 60 by 60 patches size, we get the 40 by 40 patches, totaling the 196 patches. Each patch is then flattened into the linearly projected into the 768 dimension embedding space. We add the position embedding and special classification token called the CLS token. This sequence is passes through the transformer encoder, typically with the 12 layer. Finally, we extract the CLS token output and pass it through the MLP head to get our the classification prediction. The self-attention mechanism is crucial to understand. Each patch attend to all the patches simultaneously, capturing the global relationship from the very first layer. Unlike the CSS CNN, which build up the receptive fields gradually, the attention weight shows the which patches are important for understanding each patch. In lower layer, we see the local attention pattern. In the middle layer, shows the diverse pattern, and the higher layer focus on the global semantic attention. Now let's discuss what not to believe about the vision transformer and when not to use them. The common misconception, where the myth number one describe that the VIT is always outperform CNN. The reality is that VIT requires the large-scale pre-training data on the dataset like the JFT 300 million with the 300 million images. And the second myth is VIT doesn't need the data augmentation. The reality is quite opposite. VIT benefits greatly from augmentation technique and regularization method like the uh, dropout and the stochastic depth. The myth number 3 is the position embedding in code 2D structure. The reality is that the position embedding are the learn as a 1D vector. The 2D spatial structure must learn by the model itself through the training. The myth number 4 is VIT is always more efficient. The reality is that VIT is quadratic complexity O of n square with the number of patches, which is can make it slower for the high resolution image compared to efficient CNNs. The limitation about the and the way to avoid the VIT is that there is a specific scenario where we should not use the vision transformers. So the first, when we have the limited training data, the VIT require the dataset with the 100 million or the more images for the best performance. Second, with the small computational budget, training VIT is expensive and time consuming, requiring the more powerful GPU and or TPU. Third, or for the real time application, the interface can be slower than the efficient CNN like the mobile net or the efficient net. Fourth, for the edge devices, the large model size can make the unsuitable for the mobile phones or the embedded system. Additionally, additional challenges includes the high memory requirement during the training, the need of the sophisticated regularization technique, longer training uh, times as compared to the CNN, less effective transfer learning when large datasets are small, and the requirement for careful hyperparameter tuning to achieve the good result. So let's summarize what we have learned today about the vision transformer. So the first vision transformer applies the pure transformer architecture directly to the images without any convolutional layer. This was the bold and revolutionary step in computer vision. Second core innovation is dividing the image into the patches and treating them as a sequence similar to the words are treated in natural language processing. Third, the self-attention mechanism enables the global context understanding from very first layer, unlike the CNN, which would receptive fields gradually. Fourth, for this crucial is VIT requires large-scale pre-training for the best result. The model needs to see the hundred of millions images to truly outperform CNNs. The fifth, while powerful vision transformer come up with the challenges, they need the significant computational resources, large dataset and careful tuning. So the impact of this have the transformer has created the paradigm to shift in the computer vision research. They have become the foundation for the modern vision language models like this SLIP and DAL-E. They have achieved the remarkable success in the research. So they're looking forward with increasingly becoming the backbone of the modern AI in the system is the vision transformers. So that's all about the today's presentation. Thank you.